Okay, let's start. Good afternoon. Thanks for coming. Today is the seminar number 60. So it's still nice to have always people coming. And we have Eugenio Cutolo, who's about to finish his PhD. He was during the TMOC group department of IMEDEA, and he was under the supervision of Simon and Ananda. Only you two know the directors. And yeah, he's gonna show us a bit of his work. So enjoy and sit tight.
Okay, hi everyone. So in this talk, sorry, I have to stay close to the keyboard because there is no pointer. So I'm not going to talk about ants, but a bit about ocean. That is what my PhD is on. I'm physical oceanography. But mostly I would like to talk about some hints and challenge that I face on during with an artificial intelligence technique that I've been applying mostly to ocean data, of course. But first of all, I try to use many examples since I don't want to be too much technical. There are many details. So in this presentation, I'm going to try to skip them. If you want to then have more details, you can ask me later after the presentation. Then I'm going to try to use some example. So the first one is the game of life. I don't know if you ever heard about it. It's just a way to schematize what happens from simple rules. You can generate really complex dynamics. So this is a game that is based on a grid cells, and the cells can be black or white. And according to these 4 rules that you see here on the right, you can turn on or off a cell. And so loneliness or crowding, reproduction, and stasis. And they're quite simple, but they could generalize complex. Too epic. Okay, so dynamics like this one is not can't see too much good here, but you see that looks like big city or big dynamics, but this is just the application of initial condition and these simple rules. So the idea here to take on is that complex dynamics will arise from very simple rules. And what happens now? We did this example when we know the rules, we tune the rules, but what happens when we don't know them? So one of the case, in some general sense, will be the ocean circulation, because you see that there are many complex structures. You can see some headies here in the Boran Sea where we have been doing some experiments. This is Mallorca, and you can see the northern current, Algerian current. But the problem is that we have the equation, the Navier-Stokes equation, maybe you heard about, that are impossible to solve. But in the end, they are a way to model, to try to understand what's going on there. We don't know what is in physics, you try to understand a system, trying to minimize a Lagrangian, to minimize the rules, but it's really hard for this case. So what we usually do is try to work with scales, with different phenomena. We try to box them in scales that are regarding the time and regarding distance. So, for example, climate change is something that is going on, but it's a pretty slow process compared to instead tides that are much more high frequency, or even waves that are even higher. And mostly my works is mesoscale dynamics and mesoscale. Our scale, this is the Rossby number that just gives you an idea of what are the velocity involved in this phenomenon, this process. And the problem, you can see maybe in this graph, that such process mix a lot. So it's really hard to disentangle out of different processes and to study them separately. So the starting work of my PhD that then led me to the artificial intelligence work was trying to combine different observation. One is the current velocity, and the other is the hydrographic measurements, so salinity and temperature, to combine them according to an approximated version of this equation that I didn't show you because I don't want to scare you. But it's the equation that connect them is the thermal wind equation. It's easy. Maybe you feel a phenomenon that is called Sembat here in Mallorca, and just when the land it's too warm and the ocean is cold, you have this sea breeze during the day, and during the night it changes. So this equation could also be used in the ocean, and I used this equation, this observation, to obtain a 3D reconstruction of the anticyclonic eddy that we have been sampling in the Alboran Sea. And this is, I didn't show you here all the scale of the cross scale, but it was just an idea to understand the vertical transport in this eddy. But I don't want to get too much into detail. If you want, there are in the paper. But the idea here that was really hard work, because many observation has many problems, because you have to tune the errors of an instrument and error of another instrument. And then if you want to put them in a model, in your equation, it's pretty hard to obtain a good product. So since I'm a bit lazy, I was wondering if we can automatize the process. And that's why I get into artificial intelligence, that in the end is trying to reply the behavior of our brain. So just to give you some hints, even between neuroscientists, it's hard to understand what is doing the brain. Maybe the one that achieved the best knowledge, studying a lot of mental disease and, of course, neuroimaging, is Carl Friston, a neuroscientist that wrote this paper that is the free energy principle, that it's pretty strong statements in which it says that the brain is trying to minimize the surprise. And what is the surprise is the difference between what you expect and what you get from your sense, from your feeling, from your perception. So you have an idea, you have a model of the world, and this is the only equation that I'm going to show you here. So this is the prediction that your model, your inside model has, and then this is what you get, and you try to minimize the square error. This is pretty famous, the scientific word. And so this is actually what also artificial intelligence techniques are doing. You have an input and an output, and then you want to minimize such error. But step by step, some vocabulary, because there are a lot of terms that have been used in an even blurry way. So with artificial intelligence, we refer in general to techniques that mimics the cognitive behavior of our brain. Machine learning could be even a linear fit, a linear regression. It's in the end a way to perform a task without explicit information. And then what I've been working on is deep learning, that it's a machine learning technique that is based on neural networks. So a further concept, I hope you don't suffer too much, but the idea of neural networks is that you have input layer, input data, that could be images, time series, whatever observation you have. And you want to go through these weights, to this non-linear, this is a key point, and I'm gonna talk a bit more later. So you want to go through multiplication. In the end, these arcs that you see here are just multiplication of weights. And then you obtain an output. And this output, if it's not close to what you want to update your weights. So it's just a process of updating and learning with give an example. You say, if you see this, you should tell me that. If you see a cat, you should tell me that it's a cat, and you want to update such a prediction. And in the end, you are still minimizing this function that I showed you before to the brain. And the two main elements of these techniques, one is the nonlinearity. I think to do this example, driving the south of Italy, it's easy that even if you do a small infraction, someone can really overreact. So this is nonlinearity in the end, because, for example, when in a box match you have a punch, you punch me, I punch you, it's more or less the reaction is similar to what you do. Instead of nonlinearity, the consequence of a small event, a small change in a function can explode, can be really strong. And this is fundamental if you want to correlate or to find the relation between variables that are not directly correlated with a classical linear fit, linear regression, for example. And this is a condition of the universal approximation theorem that is actually the basis of the whole deep learning techniques and work. And the other really important idea between trying to teach two networks to understand things is to avoid local minima. Maybe if you look at the horizon and you see it's flat, you can say, yeah, maybe the Earth is flat, because you have this perception. But this is in the end just that you get stuck in a minima. And another example that I think of, if you are in a Puigmayor and you want to go to Inca, you know that you have to go downhill. But then you reach Cuba and they say, okay, maybe I'm here because otherwise I have to go uphill. But this is not, because, of course, if you don't know the geography of the island. But this is just because sometimes you have to go, even in the contrary sense of what to expect. And to achieve this, the idea in machine learning is to use stochastic gradient descent. So sometimes instead of going where the gradient is the steepest, you just go randomly. And in this way, you can assimilate more information from your data. And sorry, I'm gonna give you an introduction first. So this is a bit of a concept about machine learning, but then why I use that and for doing what. So this is a problem. In the end, the problem that I try to face is common in many different sciences, especially now it's being developed a lot in medicine. The idea is that you have a lot of data, for example, images, is where do you pay attention, what is really important, where do you have to focus. And actually, there are studies, even comparing the gaze traces like with eye tracking technique, that is just trying to understand where students or experts are looking when they are looking at radiography. And you can see that the students are much more dispersed, while the experts know where to focus to find the most important disease. And so the same idea, the same capacity of focusing in the important part, I want to develop an artificial intelligence that can do that, of course, in the ocean. And the nice thing is that in the ocean we have satellites. This is SST images, surface temperature images. And I've already put some arrow to show you what to me are and to some of the oceanographic community are the interesting points that are where there are change in the property of the water. And these are the fronts. So this is the idea that salinity, temperature, or other variable change a lot in a small area, in a small distance. And these are particularly important because for vertical transport, vertical velocity is particularly relevant there. Actually, a part of my group is working a lot on that. And this is, once more, it's important because it moves tracer up and down. So CO2, nutrients, and contaminated pollutant. So pretty important. But it's pretty hard to understand such phenomena because going to the sea, it's pretty expensive. You need a boat, we need people, we need instruments, and so we don't have a lot of data. And to reconstruct such fine scale process, it's hard. You need a lot of days at sea, fast measurements. And help, of course, comes from the satellites. As I told you, gives you this idea of big picture because you can measure the sea surface temperature, the chlorophyll concentration, and now it's a satellite that has been deployed recently and we launched recently that it's also going to be able to measure the altimetry more or less in 2D. Now we already have altimetry in 1 point, so this is another information that we can use. But to use this, now it's used a lot to compare when you have to go to the sea, maybe you look for the images and try to understand where you have to go. But to me, the idea was to try to use this information more to combine the efforts of in situ work and the remote sensing work. So I don't know if you work with this technique. It's called document interpolation. It's the most common one when you have a sparse observation and you want to obtain a gridded product. So you have an observation here, and you assume with a Gaussian shape function that since this point is close to this one where you have measured, should be similar. But this, for the fronts, something that I showed you before, this is not true because in 1 kilometer you can have strong change. Instead, my idea was, since we have this big picture from satellites, you can cluster points, get a family of points. And so you will have points boxed together, stacked together in a family that share the same properties. For example, the same concentration of chlorophyll, the same temperature, or whatever kind of variable. And in general, with this, I would like the starting point with this: try to clusterize the information and extract non-local correlation. And such non-local correlation actually is the idea between you probably heard about ChatGPT. It's a way of processing human language. And it was pretty revolution because before the dominant linguistic theory for understanding language was the one of Noam Chomsky. Is a really good intellectual. I strongly recommend all his literature. And the idea was universal grammar. The idea that kids do not receive a lot of information about their language. They just hear some information, some words. So since they don't have a lot of information from the talk that they hear, they should have in their brain some hard-coded structure. So there should be already a model in their brain, biological model, and then they learn the label of the words, and then that's how they learn to speak and to their language. But this paper, this revolutionary paper, I think is the paper with most citation that I see in my work career, is instead is suggesting that non-locality to analyze human language is the key. So to be more, to make you an example, if you have a phrase, instead of the approach before, when the first model were trying to understand the meaning of a phrase going word by word. So one word and then the following one. But instead, this model behind ChatGPT and other technique, it's trying to correlate each word of the phrase with all the words in the phrase and to create a map of meaning between all the words. So you can see here, okay, this is just an example of a phrase. And this, I'm showing you, okay, this is when you have just correlating words that are close. And this is GPT, the one behind ChatGPT. And this is the same, but for the ocean of what I've been doing. So the optimal interpolation is considering a point of the ocean correlated if they are close. And instead, the clustering idea, it's relating points just if they belong to the same structure. That could be an eddy, could be a meander, or whatever. So to this idea was, I developed this idea in a neural network that is called PoiNet. And the idea is to take advantage of the big picture of remote sensing images to interpolate sparse observation, in situ observation. So to train this network, well, I'm gonna tell you later about the how I trained that, but the idea is that I give the network a surface field of any kind. I propose some clusters of the points according this first part of the network creates some cluster according to the values of these fields. And then I take insert into the network also the information of where I actually have measures. So for example, if I do CTD cast, or if I know that there in these black dots, I have such some values of my fields. And so I also put this information to the network to take into account the information that I have and remap, refine the clusters. And these clusters allows me to get the covariance that in the end, the matrix of covariance is the keyword for obtaining the interpolation, because then you can, use the shape information from satellites to reconstruct even fine structure, even fronts. So I was telling you before, the idea of neural networks that you need to train, you need data to create the network to understand the model. And so to obtain a lot of data, the easy way in the oceanographic community is to use model and generate a lot of outputs. And that's what I've been using, a model. So it's a fake ocean, but it's pretty realistic because it's not exactly the ocean that we can see in front of our window. In the end, it's just realistic because it's using the same equation, the same physics. So more or less allows me to make simulation and simulated experiments, and so collect data and train the network knowing what's the real truth. I try to sample my model, try to reconstruct the truth, and then compare with the real truth that I know because it's the model. And so I've been doing some tests, training the network with some data, and then some other data that were not part of the training. I did a check if it was working, and I compare also with the canonical technique of interpolation. And so you can see here how the RMSE is decreasing a lot, especially when you provide the SSH, the altimetry of the sea, you provide a lot of information and you can reconstruct surface fields, but even deep field. This is the true depth where I've been working. So this is all other metrics. I'm not gonna get too much into it. But also, not just, I've been using this network, not just with fake data, but also with real data, with real observation. And in particular, here we have an example. I've been using these chlorophyll images from satellites, cluster the chlorophyll images, and combine this information of shapes of small scales with temperature measurements from gliders that are this automated way of sampling the sea. And actually, this is working pretty good because I also add the SST information, temperature field. So I didn't use this in the analysis, but I have a reference. So I know what's the truth more or less. And so I could compare the results of of this analysis. And it's, even here you have, compared to the not using this information, I've been decreasing a lot the RMSE. And well, the things what I'm still working on is also based on this network, but it's the idea of, since you have the information of the connection between the ocean point, where you should go sampling. Since, as I said before, it's pretty expensive to go in the sea, sample. So the idea would be to have artificial intelligence that tells you, see an ocean image, satellite images, and tells you go there and do that in this way. And this problem is similar to if you are an artist in the Florence of the 15th century, sorry, and then maybe you should want to paint something and you want something to found you. And so there is this basic example of graph theory, or graph. And so maybe you think that you should go to the richest family that of the Florence, that are the reds, that they are indicated with the darkest colors. But no, you should go to the family that is more connected with all the other families. And that's why, I don't know if you heard, but they are pretty famous, the Medici family, because they were the more connected through weddings and other stuff with whole Florence. And so this is just an example, but to show you the idea to realize this adaptive sampling technique is that if you know that one point of the ocean is correlated with a lot of many other points of the ocean, you should go there. You should put your effort to go there. And so starting from the same baseline of the clarinet, once I have the covariance, I don't want to make a reconstruction, but instead using another technique that is called reinforcement learning, create the best path where you should go with your ship, with your robot, or whatever you have. And this, in conclusion, is similar to what actually ants do for finding the shortest way to get from the nest to the food. This is not artificial intelligence. This is called actually swarm intelligence, because all the single ants are not particularly smart. But all together, they leave pheromones through their path. The pheromones evaporate, and so the path that is the shortest should have more pheromones trace, because otherwise, since more the time passes, more the pheromones goes away. The paths that are shortest to go to the food are the way in which all the ants, they start randomly and then they converge toward the optimal path. And actually, the reinforcement learning technique that I've been using is pretty much based on that. And this is more or less everything. I didn't put so many, a lot of the results of the paper you can find in the paper here. I just want to give you some hints, some ideas, so I hopefully convince you, and maybe you know more than me with all the biology studies, that the complex dynamics could arise with really, really simple rules, and data-driven approach like machine learning could be better when you don't have idea of all the scales that are involved in such a phenomenon. And in general, they could be better of an a priori model. So when you have a model that is incomplete, could be better maybe to do, if you have enough data, of course, this is a problem, to work with data-driven approach. And in general, the idea that is working in machine learning and other techniques is that if you have a problem, you should copy how nature solve its problem or its optimization question and do the same for your. And for the moment, there's still needed work of the humans to shape these neural networks, especially to define what are the cost function, what you really want to achieve with these neural networks. But I'm not so confident to tell you that it's going to be this way forever, because there are already been developed some neural networks that they develop other artificial intelligence. It's like a recursive way. So I'm not gonna tell you this is gonna be fun, because we will see how much of work we still have. And that's everything. So thank you. And if you have any questions.
Can I ask you something? I have to say it's super interesting, but I got confused as to exactly what is the output of your AI model.
Sorry. So the input, yeah, I didn't specify. But the input is the surface field and the in-situ observation, where you actually have the wall water column. So you have the surface and the wall water column, but just in some points. And the output is the full 3D reconstruction.
So the full 3D reconstruction
Yes. Of the water property, water property could be salinity. Yeah.
So scalar fields or vectorial fields?
Scalar field, but could be definitely also vector field. There is no limitation on this. Yeah.
And you have as input, experimental input, the whole water column.
Yeah, because usually when you go into the sea, you deploy this is Rosette or CTD, you stay in a point and you measure the wall column, but just in one point because it's time. Yeah. So the idea is with this information local that is pretty complete about the wall column and the satellites that give you just the surface, obtain the 3D of the wall area. That's the idea.
So as far as I understand right now, you incorporate mainly observational data. I have once the surface field and the water column measurements. But in the beginning, you said there would be also the chance to incorporate the physics.
Yes.
So
Actually,
we don't do that yet.
Yes, the idea actually, there are two approaches, in the beginning. The data-driven approach, that is this one where you do not incorporate any kind of a priori knowledge. And then there is the old one that is you have a model and you try to assimilate data. That assimilation is called, in fact. It could be possible to do a hybrid approach. So you have a part of data-driven, and then you also try to push some physics, and actually they are called physics-informed neural network. And I'm considering this approach, to give a better representation to, if you don't have enough data, maybe you can add some knowledge. Yeah, it's totally possible, but at the moment I didn't do that. Yeah, but it's.
I think the first paper you have done.
Yeah.
Some physics.
Yes, no, in the first paper I was working with variational approach. So in the first paper, the one that I show you in the really beginning is one. Here, I didn't put the equation, but here the idea was without machine learning, but with the previous concept that was variational approach. Here I was giving the current information, so the observation of the velocity, the information about salinity density in general, and I was putting this equation, the Therman-Wind equation. So it was a kind of data-driven approach, but also with knowledge of the physics. So, but this was still without deep learning. Then, but yeah, this would be also the natural way.
Maybe it sounds to be a question because I really don't understand everything. But I have a question related with how you separate mesoscale from climate change scale.
Well,
And the amount of error that you can accumulate with your output. How you?
I mean, see this picture again. At least scales that are pretty, here you see the circles here, and for example, climate change, it's pretty far here in the right position, and so it's not overlapping a lot with mesoscale, because in the end it's a slow process and involves even scales that are pretty big, like the whole Mediterranean Sea. Usually you talk about the warming of the whole Mediterranean Sea. You are not talking about the warming of a point in Lanzarote. Actually something like that. Yeah. But instead, the real complex things is this one, because this area here, you have a lot of overlap between tides, mesoscales, waves. So in general, this is not too complex to separate the climate change from the mesoscales, because you can see that there is a trend. In the end, it's like removing a trend is not difficult. You can focus, if you want, on the trend or in the high frequency variability. And the way in which you do that usually are temporal filter or even a spatial filter. So this is the basis, and then you have many, many more complex techniques. And then, of course, there is a problem of errors. To do this work, I'll tell you a bit that was pretty hard because, for example, IDCP is measuring the total velocity of the sea. And in this total velocity, you have waves, inertial motion. So it's really crazy. You have to make some assumption and maybe try to get as many data as you have to try to resolve some scales. For example, in this campaign, we were also deploying dristers that are just buoy with GPS. And according to the movements, we can estimate what's the motion due to the inertial, to the fact that the Earth is moving. So yeah, it's hard to make estimation of the errors and to disentangle. Yes, Simon?
Well, I just would like to insist in this comment of the error. You know that we have talked a lot about this comparison between offline decoration for
Yes.
like me, that we have in 4 years, that we have been using offline decoration in a lot of years. I was this is really a revolution that you are presenting, but I would like to know your opinion about the estimation of the error, because in the case of the offline integration, you can differentiate between sampling errors, estimated errors, but here. So I know a little bit what is behind, but I would like to have your opinion about this issue of the errors.
Yes, well, so at least for the reconstruction error, this is the same as optimal interpolation, because as soon as you obtain the covariance matrix, then you can use the same exact formula of the optimal interpolation. Yeah. So in the end, if you are confident of the information that the satellites gives you, of course, you can also propagate if you have an error field of the satellites, you can also propagate such error into the covariance matrix. And then with the covariance matrix, that can also integrate the error of the in-situ observation. You have, it can be it's hard to explain, but in the end, it could be change a bit the shape of this graph. So if you have height error, in the end, your covariance is going to be. One point could be correlated with many more points. So if you have strong error, if you say, okay, I'm going to give you this field of the surface, but my confidence in it is pretty bad. So even the covariance is going to be more or wide. So in the end, you're going to miss. Maybe you can reconstruct a good field, but then the error is going to be. So yeah, there is in the end, the direct relation between the error that you give and the error that you obtain in the reconstruction. It's a mathematical formula in the end. And then if you want to minimize the errors, this could be part of the adaptive sampling idea, that as soon as you collect more information, your error decrease, your confidence in the data increase and the error decrease. And so this is actually part of the idea of adaptive sampling, trying to tell you where you should go to minimize the error, the final error. Yes.
No questions? Thank you.
Ya, tenía una animación de las hormigas que se movían, pero.
Yeah.
And I was